A doubly linked list DLL is like a two-way street where each car node can go forward or backward. Each node stores three pieces of information. Data, the value the node holds, for example an integer, a string, or an object. Next, a reference pointer to the next node toward the tail of the list. Prev, a reference pointer to the previous node toward the head of the list. Visually, head to node A to node B to node C to tail. The head pointer points to the first node, the tail pointer points to the last node. Because each node knows both its successor and predecessor, we can move in either direction without starting from the head each time. This bidirectional linking is the core structural difference from a singly linked list, which only has a single next pointer. Insertion at the head puts a new node in front of the current first node. Algorithm pseudocode. Function insert head takes a value. New node equals node of values. If head is null, head and tail become new nodes. New node next and previous are set to null. Otherwise, new node next points to head. New node previous is null. Head previous points to new node. Head becomes new nodes. Pointer updates are constant time, only 4 assignments are needed regardless of list size. Empty list handling is covered by the if head is null branch, where the new node becomes both head and tail. Time analysis, the number of operations, does not depend on n list length, so T insert head of n equals C implies big O of 1. Numeric example, suppose the list is 10 linked to 20 linked to 30 head equals 10 tail equals 30 inserting 5 at the head. New node next equals 10 new node previous is null 10 previous equals 5 head equals 5. The list becomes 5 linked to 10 linked to 20 linked to 30, only 4 pointer writes were performed. Insertion at the tail adds a node after the current last node. Having a tail pointer makes this operation symmetric to head insertion. Algorithm. Function insert tail, open parenthesis value close parenthesis colon. New node equals node open parenthesis value close parenthesis. If tail equals null colon empty list. Head equals tail equals new node. New node dot next equals new node dot prev equals else colon. New node dot prev equals tail step 1 colon point back to old tail. New node dot next equals null step 2 colon nothing after new node. Tail dot next equals new node step 3 colon old tail points 4. Tail equals new node step 4 colon update global tail pointer. Single node handling is automatically covered colon when the list has one node, head and tail point to the same node, and the same steps correctly link the new node. Time analysis colon only a constant number of pointer writes, independent of n colon. T insert tail open parenthesis n close parenthesis equals C implies O of 1. Numeric example colon list is 10 double arrow 20, head equals 10, tail equals 20. Insert 30 at tail colon. New node dot prev equals 20. New node dot next equals 20 dot next equals 30. Tail equals 30. Result colon 10 double arrow 20 double arrow 30. 4 assignments again. Insertion at the ith index, 0 based, means placing a new node between the nodes currently at positions i-1 and I. Algorithms. Function insert at index value. If index is less than 0, error. If index equals 0, insert head with value and return. Optional, maintain a pointer to tail to allow quick tail inserts. Set current to head. For k from 0 to index -1 do. If current is null, error out of bounds. Move current to current next, after the loop current points to the node at position index. Now current is the node that will become the successor of new node. Previous node equals current previous, node currently at index -1. Create new node with values. Set new node previous to previous node. Set new node next to current. Set previous node next to new node. Set current previous to new node. Traversal steps. We walk from the head until we reach the target position. This costs index pointer moves. If index equals size, the loop lands on null and we can treat it as tail insertion. Out of bounds, if the loop encounters null before reaching the desired index, the index is larger than the list length, raise an error. Time analysis. Insertion time equals theta of I plus theta of 1 for traversal and constant relinks. In worst case, I equals n gives theta of n. Numeric example, list 10 double-20 double-30 size 3. Insert 25 at index 2 between 20 and 30. Walk start at 10, k equals 0, move to 20, k equals 1. Stop, current points to 30, previous node to 20. Relink, new node previous set to 20, new node next set to 30, 20 next set to new node, 30 previous set to new node. Result, 10 double-20 double-25 double-30. 4 pointer updates plus 2 moves, order 2 approximately order n for n equals 3. Deletion of the head node removes the first element. Function delete head, open parenthesis, close parenthesis, colon. If head equals null colon error empty list. If head equals tail colon single node list. Head equals tail equals null. Return. New head equals head dot next. New head dot prev equals null. Head equals new head. Pointer updates only 2 assignments new head dot prev equals null and updating head. Single node case both head and tail become null emptying the list. Time analysis constant work independent of n. T delete head of n equals c implies O of 1. Numeric example list 5 to 10 to 15 delete head 5. New head equals 10. 10 dot prev equals null. A head equals 10. Result 10 to 15 only 2 pointer writes performed. Deletion of the tail node removes the last element using the tail pointer. Function delete tail. If tail equals null, error empty list. If head equals tail, single node list, set head and tail to null, return. Set new tail to tail dot previous. Set new tail dot next to null. Set tail to new tail. Pointer updates, 2 assignments new tail dot next equals null and updating tail. Single node case, same as head deletion, list becomes empty. Time analysis, t delete tail of n equals c, yields big O of 1. Numeric example, list 10 linked to 20 linked to 30, delete tail 30. New tail equals 20. 20 dot next equals null. Tail equals new tail. Result, list 10 linked to 20, again only 2 pointer writes. Deletion at the ith index removes the node positioned at I0 based. Function delete at index colon. If index less than 0 or head equals null colon error. If index equals 0 colon delete head, return. Cur becomes head. For k from 0 to index colon. If cur equals null colon error out of bounds. Cur becomes cur dot next after loop cur points to node to delete. Prev node becomes cur dot prevs. Next node becomes cur dot next. If prev node is not null colons. Prev node dot next equals next node. If next node is not null colon. Next node dot prev equals prev node. If cur equals tail colon. Tail becomes prev node. Traversal colon same linear walk as insertion costing theta I steps. Edge cases colon. Deleting head index equals 0 handled separately. Deleting tail cur equals tail updates the global tail pointer. Single node list both head and tail become null. Time analysis colon. T delete at ni equals theta I plus theta 1 gives worst case theta. Numeric example colon list 5 arrow 10 arrow 15 arrow 20. Delete at index 2 value 15 colon. Walk 5 to 10 to 15 k equals 2. Prev node becomes 10, next node becomes 20. Relink 10 dot next equals 20, 20 dot prev equals 10. Result 5 arrow 10 arrow 20. 4 pointer updates plus 2 moves big O2 approximately big O n for n equals 4. Space colon each node in a singly linked list stores 1 pointer next. In a doubly linked list each node stores 2 pointers next and previous. If a pointer occupies p bytes then for n nodes. Space singly equals n multiplied by the sum of data size and p space doubly equals n multiplied by the sum of data size and 2p, which equals space singly plus n multiplied by p. Insertion colon. Head colon both structures need big O of 1 time. Doubly linked list also updates previous of old head, which is an extra constant. Tail: singly linked list without a tail pointer requires big O of n to reach the end, while doubly linked list with a tail pointer is big O of 1. Middle: singly linked list must traverse to position I, theta of I, and then only adjust one next pointer. Doubly linked list also traverses theta of I, but must adjust 2 pointers next and previous. The asymptotic time is the same, theta of I, but the constant factor is higher for doubly linked list. Deletion: head: big O of 1 for boths. Tail: singly linked list without a tail pointer needs big O of n to find the predecessor. Doubly linked list big O of 1 using previous. Middle: both need theta of I traversal. Doubly linked list updates 2 links, singly linked list updates only 1. Mathematical summary, ignoring constant factors: insertion head big O of 1 for both. Insertion tail big O of 1 for doubly linked list, big O of n for singly linked list if no tail pointer. Insertion I big O of I for both, I less than or equal to n. Deletion head big O of 1 for both. Deletion tail big O of 1 for doubly linked list, big O of n for singly linked list if no tail pointer. Deletion I big O of I for both. Extra space per node plus p bytes for doubly linked list. Thus, doubly linked lists trade extra memory for faster tail operations and symmetric bidirectional traversal. Starting with an empty doubly linked list, perform the following operations in order. Insert tail 10. Insert head 5. Insert at 1-7, list becomes 5-7-10. Delete tail. Insert tail 12. Delete at 0, delete value 5s. Insert head 3. A. Draw the list after each operation, showing previous and next pointers. B. Count the total number of pointer assignments performed across all operations. Solution outline. Step 1, list is 10. New node.next equals null, new node.previous equals null, head equals tail equals new node 3 assignments. Step 2, list is 5 linked to 10. New node.next equals 10, new node.previous equals null, 10.previous equals 5, head equals 5 4 assignments. Step 3, list is 5 linked to 7 linked to 10. Traverse to index 1 move relink. 7.previous equals 5, 7.next equals 10, 5.next equals 7, 10.previous equals 7 4 assignments. Traversal does not count as assignment. Step 4, list is 5 linked to 7. New tail equals 7, 7.next equals null, tail equals 7 2 assignments. Step 5, list is 5 linked to 7 linked to 12. New node.previous equals 7, new node.next equals null, 7.next equals 12, tail equals 12 4 assignments. Step 6, list is 7 linked to 12. Previous node equals null, head case, next node equals 7, head equals 7, 7.previous equals null 2 assignments. Step 7, list is 3 linked to 7 linked to 12. New node.next equals 7, new node.previous equals null, 7.previous equals 3, head equals 3 4 assignments. Total assignments equals 3 plus 4 plus 4 plus 2 plus 4 plus 2 plus 4 equals 23. The final list is 3 linked to 7 linked to 12, with head pointing to 3, tail pointing to 12, and each node's previous and next correctly set.